Pharmaceutical Processing, in conjunction with INTERPHEX 2016, presents INTERPHEX Live.
With Mark and I mean, what we're going to, Mark is the regional sales manager for the Alpha level and catheter dehumidification, okay? Now, if anybody had caught the discussion we just had, one of the things that we were talking about was tech transfer and sometimes our inability or our ignorance on infrastructure. And I got to tell you, from my standpoint, Mark, one of the things that a lot of process guys do, because they're not all chemies, or engineers for that case, a lot of them are physical chemists or pharmacists, is the concept of humidity and concentrate, relative humidity, things like this. And because I've seen some requests that will make your hair, well, as you can see, my hair fell out. But like, I don't think they've really grasped in a lot of cases what it's about. So like I had said, we're going to talk, we want to touch on some of that. So we'll go back to 101. And we'll start there, and then we'll start to move into some of that. I think one of the key pieces that we should talk about, I mean, to give you some of the craziness I've seen, people will, we're in a standard facility, right? And they decide that, well, they need, the room I'm running this product in, because it happens to be somewhat hygroscopic, it has to be at 20%. Now, I always look them in the eye and I said, you do understand what you're asking for, right? Yeah. So from our end, there is parts of science that can tell you that. What is the equilibrium moisture concentration of this at plant conditions? So, I mean, from our end, there's certainly things that we can ask that say, well, that's unrealistic or it's realistic, because the chemistry tells it. But in a lot of cases, sometimes there is no option. Okay, as you guys know, you're in that business. So after I beat them up and say, you're asking some stupid stuff off the cuff, but if it turns out this is a real process condition, then I say, okay, then we got to talk about Psychometrics 101. So with that, Mark, I think maybe what we got to talk about a little bit is, all right, I'm air conditioning this room, but I want this room to be 20%. So why don't we walk through that? All right?
Yeah. If you're looking at just this room, you just need general, it's comfort conditions. It may be 70 degrees, 50% RH is what you're trying to achieve in this room, and that you can do with just your general air conditioning equipment. There's nothing special about it. It's a refrigeration coil, and you're going to use that to be able to provide the comfort cooling conditions in the space. But if you start to, if you're going to want 20% RH, 30% RH in the room, then you're going to have to start looking at using a desiccant dehumidifier. And with a desiccant dehumidifier, you're going to be able to achieve lower dew points with that technology. A desiccant has a natural affinity for water, and it's going to be able to supply humidity conditions that are going to achieve 20% RH. So, basically, if you're looking at some, conditions that are below a 45-degree dew point, that's when you're going to want to start using desiccants. And if you were trying to use your general air conditioning equipment to achieve those conditions, you're going to have higher energy consumption, and it's going to be, you're going to be driving that temperature of the coil of the air conditioning equipment way down in order to achieve those humidity requirements. So, but with a desiccant, you can achieve below a 45-degree dew point pretty easily. And then when we get to 20% RH, that's even drier. You definitely want to be able to use a desiccant, because your energy consumption is really a big player with that.
So, I mean, I think the limitation on refrigeration is the best I can do without moving, in other words, in a standard infrastructure, and you guys have built and put together more pharmaceutical companies than anybody else, I would think, on that area. Standard refrigeration, standard air conditioning, the best I can do is 40 degrees, 40% relative humidity.
Yes, right around there. I mean, it's going to be, if you're talking 70 degrees, 40% RH, then that's going to be the threshold where you're going to start wanting to use a desiccant in order to achieve those conditions. So.
Right. So, and I think, the point being is, so we're talking what, about 11 degrees C dew point, something like that?
Yeah, that would be,
Okay.
Yeah, exactly.
So I think the key is, sometimes I think the relationship, I think a lot of people feel, if somebody is knowledgeable in the area of this, psychometric understanding of what relationship it is. They think by jacking the temperature up, it's going to help. That's not going to increase drying rates for processes.
Exactly, yeah.
Yeah.
The dew point is still,
Right.
it's absolute humidity is what you're looking at. And just because you raise the temperature doesn't mean that you change the absolute humidity, the humidity ratio of how much moisture is in the air. That didn't change. Your RH changed because relative humidity is dependent upon temperature. So, but if we're looking at dew points, and you want to get down to those lower dew points, that's when your desiccant is going to be a factor. So,
Just out of curiosity, most of the processes I've worked on, we control around a dew point, relative humidity. We don't use that. Is anybody, do I have, no, yes, I guess no opinion? Okay. The reason we use dew point is it's there. That's an absolute. In other words, if I know my process is not going to, and we've done this, especially in like cast films or films that we know are reactive, we found that concentration, that amount of water and whatever we got doesn't matter. So even if I ran my process at 80, the water's still there. The bottom line is, and I can't run my bed temperatures up so high. Okay, so the answer is you got to get rid of it one way or the other. It's, people and everybody else say, I've had this argument, Mark, I couldn't tell you how many times with engineering, and the answer is it's the chemistry that's driving this, okay? So so let's start to dig into it a little more. I think we got that pretty well said. So you talked about desiccant, so why don't we talk about that a little bit more?
Yeah, a desiccant, it has a natural affinity for water. So it's a hydroscopic substance that has a natural affinity for water. And when it basically works on vapor pressures. So if you have a water molecule, that's going to be an area of high vapor pressure, and then a desiccant creates an area of low vapor pressure. And then when the two come in contact with each other, you're going to have that natural, it's going to want to gravitate from that high vapor pressure to the low vapor pressure. And then when we look at desiccants, though, we want to use that in a HVAC system. It's going to be in the form of either a dry desiccant wheel, where there's silica gel, and you might be familiar with the silica gel packets that you see in electronics or in certain packaging that you see. Well, that silica gel can be impregnated into a desiccant wheel, and then you bring air through that desiccant wheel, and the water molecules are going to attach to the silica gel, and then you need to reactivate that desiccant. So you use heat to drive the moisture out of the desiccant, and it's a continuous cycle. So you have dry desiccants, which are going to be in the form of a desiccant wheel in your HVAC system, or you're going to have a liquid desiccant. And a liquid desiccant is going to be a solution, it's a salt solution, lithium chloride and water, or calcium chloride and water. And what we do there is where you bring your process air and it comes in direct contact with the liquid desiccant. And we cool and dry the air directly with that liquid desiccant. And then so if you want 70 degrees and 20% RH, you can do that directly with the liquid desiccant, and then that you deliver that to your process environment or over the product directly to dry a certain product. And then you need to regenerate that desiccant. So there's also another component that will use heat and heat the solution up, and that gets transferred back. Once we concentrate the solution, it gets transferred back over to the process side to condition the air. So you have two technologies. You have the dry desiccant, and then you have the liquid desiccant. And, you're going to use one of those two components when you need to get to those lower dew points. So.
I think most folks, and again, in most companies, they try to assure that they define plant conditions. Mm-hmm. Plant condition is usually 25 to 30 degrees centigrade, and about 10 to 11 degrees C on the dew point side, at best. Maybe no, it's probably higher than that. It's probably more like, it's probably higher. The concentration a little higher, like 40%, but that would be on RH scale. The bottom line is you're trying to trade off and hold things, and that's usually where stability studies are done, right? So what I'm trying to say is this has an impact on products, and now we've talked about how can we make plant conditions? In other words, everybody does their stability study at those conditions. It's considered plant conditions. All the chemistry should be done. All the equilibria should be done. All right. In other words, we're assuming these guys have done their job. All right. So let's assume that they've done their job. It turns out I can't hold that condition. So let's talk about the two options you did. So when and where are these things used? So let's talk about the dry desiccant first. Is that essentially an easier answer, or walk us through that?
Yeah, sometimes you do want to use a dry desiccant. If it's a warm, dry application. So let's say when you use a desiccant wheel, the air coming off the wheel is going to be warm. It's going to be warm, but it's going to be at the right dew point that you need. So if your application calls for, it doesn't matter what the temperature is, then a desiccant wheel right off the bat seems like it could be the right approach to use, in a certain application. And then in liquid desiccants, you're going to be looking at, if you have a cooler application, 60, 70 degrees Fahrenheit, and a low dew point, then you might want to use a liquid desiccant. In that respect, we're looking at the energy consumption between the two. Another thing you might want to look at, though, is what's going on in your process environment. So in soft gels, you have oils that are going to be in the airstream. When you're encapsulating the soft gel, you have oils that will get into your return airstream and get back to the desiccant system. So one thing you want to look at is how are those oils going to impact your desiccant dehumidification system. With the desiccant wheel, sometimes you can have those oils get onto the wheel if you don't filter it properly, and then when it gets into the reactivation section, that's going to heat the wheel up, and you're going to cake that oil right onto the wheel. With a liquid system, you don't have to worry about that. The liquid system, it doesn't get bothered by the glycerin, the oil that's in the airstream. So a lot of times we look at that factor, and especially in encapsulation areas, we'll use the liquid desiccant because of that. So
encapsulation areas invariably are defined spaces. But let's just say, generally speaking, is the desiccant, let's take soft gel out of the equation. Most of this is going to be simply dust or dried conditions. Maybe it's going to be, the product's going to be in a container where they're going to circulate the air through to anneal something. So from a volume standpoint, desiccants, or is there a limitation? Is there, in other words, if I asked I have to have this, so is there a limitation on how much I can do, or?
As far as
volumes of air.
As far as volumes of air, the systems can be anywhere from upwards of 84,000 CFM you can do in one unit. So with the liquid desiccants, I'm
okay, but on the dry desiccant?
On the dry desiccant, I've seen systems upwards of 60,000 CFM, but that can be a little bit more difficult when it gets up into that
that's
air.
pretty hefty.
Yeah.
I didn't realize
I
that.
typically see it a little bit lower though. For the wheels. Lower than 60. That would be an extreme case.
I've seen, and the reason I asked the question is the desiccant wheels we've used essentially were confined processes where we tried to drop down. So what we did was you drop down the volume, bounced up the static pressure, so I got more fluid, not fluidization, but airflow. And because, I learned it the hard way, otherwise I wind up with a desiccant system that is unwieldy at best. What I'm trying to build up to is I think, so what do you tell your clients? Based on need, do you direct them towards a dry desiccation first, or a dry desiccant?
It kind of goes back to what's in the airstream a lot of times. If it is a dusty or dirty environment, the liquid desiccant seems to react a little bit better in those circumstances. So,
okay, so it's not necessarily driven by volume needed.
Yeah, not necessarily.
Okay.
When I do get above 15, 20,000 CFM, I again tend a little bit more towards the liquid system. When it's below that, then it can be kind of goes either way. But when you get up into a little bit higher airflow, then I do see liquid desiccant systems being more energy efficient and a little bit easier to handle that volume of air in a liquid desiccant system.
So in our, I mean, so what do you normally see? In other words, so just to give us a sense of it, or in the oral solid dosage form, again, soft gels aside now, and we'll get into that, for sure, because it's a sweet spot for me too. But on the oral solids, and we're assuming that you have dust collection and all. Is that the stuff you in place is predominantly dry desiccant, or?
It's probably
It's,
about
again,
it's about 50-50. If you
Yeah,
have the
okay.
right filtration, I would say, and a lot of times it does, we kind of like to present all those factors to the customer and let them know, like, here's the energy usage, here's what you're dealing with in terms of filtration you're going to need for this system. And then, from there, do they look at the first costs, or do they look at their energy consumption? What's valuable to the customer, and and go from there. So, so it can kind of go either way in other, if you're looking outside of soft gel.
Okay.
So.
One of the things that we had talked about, Mark, I mean, obviously there's liquid dehumidification and there is refrigeration and there's that's pretty much the three.
That's going to be your
Those are
main,
the three go-tos,
yeah,
right?
when you're,
Okay. So. Yeah. All right. And I think one of the things we need to touch upon, and I think a lot of times, I think what happens is we do a really good job of filtering stuff usually, but I think the reason we do a really good job is we usually do that because of other reasons. Yeah, I don't think we think about downstream or upstream equipment. And the reason we do is because of containment. We do it for safety. I mean, obviously. But I think one of the things that we know can make its way into the system, because that was one of the first things, I'm going to, again, share a story, but one of the first things I was assigned to do, apparently, when you talked about the soft gel and the, just so in case somebody is not familiar, is everybody familiar with the way soft gels are made? I mean, they have a liquid seal, which means when they're done, they're coated in mineral oil, okay? Hopefully. So what that means is there is a lot of that in the environment. So a lot of companies, what they do is they create tunnels, and however, being fresh out of college, I didn't realize that it makes its way into the infrastructure. So one of the first things was working with the folks at the time because we had a significant problem with the mineral oil, because we did a lousy job of keeping it out of the airstream, and that was so essentially the catheter system itself was the biggest, something that I was assigned to work on. Having said that, so let's talk about soft gel. Number one, when you go in and you try to advise people, soft gel has to be part of the. Why don't we talk about why you use it for soft gel? You want to touch on that for the dosage form? Why don't we talk about that first?
If you're looking at the different areas within soft gel production, the main areas where you want to have the tighter humidity control is going to be in the encapsulation rooms, and then also your drying tunnels, and then a lot of times we also use it in packaging or inspection areas. Those will also be 70 degrees, 35% RH when we're looking at packaging or inspection areas. And then if we look at the encapsulation, that's going to be about, again, 70 degrees, 72 degrees Fahrenheit, and 35% RH. And then when we get to the drying tunnels or drying rooms, a lot of times they're set up as tunnels where the product is actually on trays, and then they circulate through those tunnels. That condition will be about 75 degrees and anywhere from 15 to 20% RH. So it's gonna be a lot drier condition. And then what we're gonna look to do is supply that dry air into the drying tunnels and maintain that 20% RH throughout the tunnels. And you'll get about, we'll deliver air through the tunnels, and it'll be about 150 feet per minute to 200 feet per minute over the product to help dry and get that desired capsule weight and desired moisture content at the end. And then sometimes we'll even take that air from drying and cascade it over to the encapsulation areas. Because here we have very low humidity in the drying tunnels, and we'll just cascade that back over to encapsulation areas, and then return that air back to the desiccant dehumidifier. So that's kind of the setup, though, that you have.
What customarily, what temperature they hold this? Temperatures they usually working at?
In the drying tunnels, you're looking at about 75 degrees, and then in encapsulation, it's usually around 72 degrees Fahrenheit. So, and so if you're in the drying tunnels, you are going to get an evaporative cooling effect from your capsules. So as it comes off the dehumidifier, we'll heat the air up to compensate for that evaporative cooling. And then from there, if we're going to return that air to the encapsulation machine, where the encapsulation machines are, we'll have an air handling unit that'll just do temperature control only. You have already that low dew point air from the drying tunnels, and then now all you have to do is just run a typical air conditioning coil to drop the temperature back down to compensate for the sensible loads that are in the encapsulation rooms.
So for the most part, in soft gel, because of the discussion we just had about the existence of the mineral oil, what has been the technology that you guys put out there for that? Is that predominantly liquid?
Predominantly liquid, because if we want to be able to use that return air from encapsulation, that's where we're going to see a lot of those oils get picked up in the airstream. And so we'll return that air back to the liquid desiccant system, and those oils don't impact the liquid desiccant itself as much as it would impact maybe a wheel. With a wheel, I'd want to have a lot more filtration to make sure I take out all those oils.
Okay.
So that's why we kind of tend a little bit more towards liquid desiccants in that application.
Well, obviously, is there a down? Does it have the efficiency for, let's just talk about it. So how long, so obviously a desiccant wheel is going to have a very finite lifetime. I mean, it would depend on volume and all of it.
Right.
But what happens, it has to be changed out, right?
Yeah, I mean, a wheel could last 7 to 10 years usually. Is typical lifespan of the wheel. With the desiccant solution for liquid desiccants, the life expectancy is actually infinite for the desiccant solution. Typically, they'll have some solution on hand just to put into the system, but they don't have to take the whole liquid out and put a whole new charge of liquid into it. That's not required. So,
I gotcha.
Yeah.
So we, it's pretty clear. I mean, desiccant wheel stuff is drawn through the wheel. How does it get drawn through the liquid? How does that work?
Oh yeah. So as you have air come in through what we call a conditioner, it basically looks very similar to like a cooling tower, where we use cooling tower packing inside this conditioner, and the liquid is going to be flooded over the packing, and air comes up through this packing, and it comes in direct contact with the liquid desiccant. And that liquid desiccant is cooled inside of a plate and frame heat exchanger to a certain temperature. And then the liquid desiccant is also at a certain concentration, and with those two parameters, we can get you whatever grains per pound of moisture you need for your process. So it's a matter of direct contact with the desiccant solution in order to dry the air, and then you get a cooling as well.
So, and how do you contain the desiccant solution in that tower? How does that work?
Yeah, it's basically like your air handling unit. It's a fiberglass housing, and that fiberglass housing contains the solution, and then you have a pump that pumps it through a heat exchanger, and then you also have a regenerator too. It's a separate component that's going to regenerate the desiccant, because as we pick moisture up out of the air, our solution's becoming more dilute. So that regenerator's goal is going to be to drive that moisture out of the desiccant and send it back over to the conditioner, so that it's a complete cycle, and you don't have to put more desiccant into it.
So I guess just because in this industry, obviously, but everybody always wants to make sure that one thing doesn't get into another thing. So what I'm saying, so we got this stuff cascading in the classic cooling tower kind of deal.
Yeah.
How do we make sure that when the air coming out doesn't carry in that with it?
Sure. Yeah. There's a two-stage eliminator.
Is that a fair question?
Oh yeah, okay. Definitely. Yeah, and we're so a lot of times people are wondering. They're like, well, this air is coming from the system and delivered right over a product, and it's a product that's being consumed. So the desiccant solution does stay within the system, and we have a two-stage eliminator section that sits up on top of, right before the process air leaves the conditioner. And that two-stage eliminator section works on an impingement process. The first section of the eliminator is what we call a Z-bar. It forces the air to go in a zigzag pattern through it. Droplets will hit the sides of that and fall back into the conditioner. And then on top of that, we have the second stage, and it's just a pad, and that pad will catch anything that does get past the Z-bar. And then, and that efficiency allows, no droplets of air to leave the liquid desiccant conditioner, and you can have that air get delivered right over the product and not have to worry about any carryover. So,
just out of curiosity, when you regenerate, is it a distillation process, or how does this thing work?
it's well, what it is, it looks very similar to the conditioner. It's still a tower. It has a plastic ball packing inside of it, and as we circulate the solution through the regenerator, we're heating it up in a second heat exchanger. So we'll use steam or hot water, and as our desiccant solution becomes more dilute, the level is going up inside the system. That level will send a signal to a steam or hot water control valve and allow more heat to heat the solution up. And by heating the solution up, we're reversing that vapor pressure. And now air from outside will get drawn through the regenerator. And as that air comes in contact with the warm solution, the moisture will come out of the desiccant and be transferred to that airstream and exhaust outside. Now you have concentrated solution falling to the bottom of the regenerator that can be sent back over to the conditioner.
I got you. How about from a user standpoint? In other words, we're talking about, this is the stuff that majority of us, process guys, unless something goes wrong, this is something that's part of the infrastructure. Mm-hmm. What does the user interface look like and stuff with this?
Yeah, there's always a control panel that you can have different parameters you can set. Temperature. You can see just the different levels, and that's all user based. You can get in and work with the system in that sense. And as far as maintenance is concerned, usually just making sure that your concentration of the solution is where it needs to be, and then you're taking care of fans and pumps and stuff that's pretty typical for your utilities department.
So on a comparable basis, I mean, refrigeration versus, let's talk about liquid. So what are the cost factors here? I mean, from an energy standpoint, infrastructure, maybe just so people can get a sense of it. Because like I said, you want to understand before you go down the road. I'm sure you guys, but I think here gives us an opportunity. Let's talk about it.
Yeah.
Right?
Yeah. If you're looking at your conventional system, you have a coil and you have a fan and that cooling coil, and then you have a heating coil and your fan. That's obviously that can only get you so far. So when you do make that decision where your process conditions are going to require lower dew points and you're going to need a desiccant system, you're going to be taking care of your desiccant solution. That's going to be something a little bit very different from just taking care of a conventional coil. But outside of that, you're just basically looking over that desiccant solution, taking care of that. And the system itself will clean it. So you have a filter that's filtering that solution. That's another thing that they would have to take care of is that solution filter, and it's basically works like the oil filter in your car. It's just a cartridge filter, and it runs a small bypass of solution through that filter. So that would be one extra thing that they would take care of as well. Besides that, you're going to be looking at air filters, which are still going to be on a conventional refrigeration system. So there's a few more things that you're going to be looking after, but the system is also driving that dew point down a lot further than what your typical system can. Right. So there's
incremental costs. I got it.
Yeah.
So bottom line is, the reason it's reasonable to say to do. If you want to look at 20%, you're going to pay the difference to get that down off from refrigeration.
You are, yes, you are, definitely.
Right. That's not a downside. Understand that. Mm-hmm. I think then the client or the user has to be aware that it's imperative that they define how much of that they need. Mm-hmm.
So
What other moisture, what other factors come into play? Quite honestly, I was always a moisture fanatic because we had a very, very sensitive product. And this film was. I went to the point where I had a weather station outside Building U where we used to run our process. And the reason for that was I wanted to know what I was challenging my equipment with before I started conditioning it. Because to me, it was incumbent upon me before I start setting conditions so that I had to know. So, what I'm trying to say is, what other load factors come into play? I mean, obviously there's the weather, but let's talk about that. I mean, I think, Mark, all I'm saying is I think a lot of, I'm sure you get these calls. To me, the misunderstanding that drives a lot of this stuff,
Yeah.
So let's talk about, what other things or factors here that you, as an expert in the area, talk about?
Yeah, when we're looking at, if we're drying a product like we are here in soft gels, there's going to be a product load. So we're going to want to look at how big is the capsule that we're making, and what is the moisture content, the desired moisture content when it's finished, when it's leaving the drying tunnels. So we're going to look at that difference in moisture content, and we're going to look at how many capsules per hour you're producing, and that's going to drive what a certain BTUs of latent load for the system. So that's one thing for sure, is going to be the product load and how we calculate that. Another one is going to be infiltration from outside. So if you're trying to control a space, and on the other side of that wall is going to be an area where say it's a hallway that's just comfort cooling conditions, 70 degrees, 50% RH, but then you have this area that you're trying to maintain 75 degrees and 20% RH. Moisture is naturally going to want to gravitate into that space. So there's infiltration, permeation loads, and then as doors open and close, that's going to be infiltration as well. Moisture wanting to gravitate into that space. So we have to look at all that, and then people also are a load, a latent load, a moisture load. 600 to 700 BTUs per hour of latent load just given off from one person. So depending on how many people are involved in the process, that will be another factor. So looking at all those, those are kind of all the things we're going to look at as we're coming up with the total latent load that the dehumidification system is going to have to handle.
So for a typical process, how much moisture are we talking about? I mean, soft gel predominantly is a 24/7 deal, but
right.
So just give it, help me out here. What kind of numbers are we talking about? Is that a fair question?
Yeah, I mean, it all depends. Sometimes that can be tricky because I'll have.
Well, let's assume they're not making paintballs. All right. They're making something. All right.
Yeah.
Let's talk vitamin E or something.
Yep.
All right?
Yeah.
Okay.
Yeah. Well, let's say they have. Let's say they have two machines running,
right.
Two encapsulation machines, and they could have maybe 10 pounds per hour of moisture per drying tunnel, or for, in that application, it's probably about maybe 10 pounds just for the drying tunnels. It might be a little bit more in the encapsulation area as well,
right.
Because encapsulation, you might have people involved. You're conditioning an entire room, and then that encapsulation machine is going to be drawing that air in to the tumble dryers as those capsules are being produced and then going through the first stage of drying. So,
right.
It's maybe typical, maybe around 10 pounds per hour in just the drying tunnels, and then I would say maybe closer to 20 pounds per hour in the encapsulation room. Again, with a lot of that, depending on how much product we're trying to produce, and is it a 24 oblong capsule, or is it a 10 oval size? It all depends on. There's a lot of factors that go into it. So.
Oh yeah, no, there's a lot of factors, and I think one of the things, at least when I was in soft gel, that we tried to do was to make our lives easier, was to put all the load in one spot. Mm-hmm. So we would try to linearize it. You'd put the machine, you put the degreaser, the washer, and then you would put the dryer. You'd line them all up in the same tunnel. Yeah. Is that what you see customarily?
I see. Typically, I'll see like the encapsulation room, and then right after that, you're going to have the product get transferred onto the trays, and then those trays brought right into the tunnels. Mm-hmm. So, and that will be we'll get that as close as possible. In those areas, so that would be ideal.
So, in general, what's your first go? In other words, somebody says, and let's take for this time, let's take soft gel out of the equation. So, as an expert in the area, what is your usual recommend? What's your first recommendation? What do you tell them?
Yeah, I usually like to look at the liquid desiccant because of energy consumption. You know, a lot of times I end up seeing about 20 to 30% energy savings. You know, that's not every case. You know, I'll definitely look at it case by case, but there's a lot of times where the energy savings will be there with the liquid system. And on top of that, if I'm drying a product, the liquid system is going to kill bacteria and viruses. So, you know, the liquid itself has biocidal properties, and if we're delivering air over something that's consumable, whether this is pharmaceutical or if it's or whether it's candy, I like the fact that the liquid system can kill bacteria and viruses, so that that's an added benefit really to the whole system. Whereas I can't really, the Desiccant Wheel, I don't actually have that capability to kill bacteria and viruses. So energy, how it cleans the air, those are big things that you know, liquid desiccant definitely does have those advantages. So that when I look at things, that is kind of my first go-to. But it might not be the case for every application. So definitely need to look at you know, what kind of conditions, how low of a dew point it is. So if it's extremely low dew points, then you might need to go with dry desiccant systems. So, but overall, I'd say the liquid system, because of energy and the cleaning the air. So.
You know, in this industry, we like to look for trouble, but we keep talking about it. And a lot of times, a lot of it is because we ignore it, or it's ironic. We ignore what's going to get us, but in a lot of times we don't look for the things, and then we drill into stuff we shouldn't really drill into because it's not going to be a problem. Only because I've been vexed by so many quality types, air quality guys. They monitor everything under the sun. So, have you ever run into the situation where they come out and you say, you know, Mark, geez, you know, we're monitoring the air quality in here, and gee whiz, you know, you ever see anything that would result in some, you know, has it created a problem? Any of these people? I mean, it's killing bugs, but on the same time, what else is it? It's not putting anything else in, right? That's where I'm at.
It's not. Yeah. You don't have to worry about that. Any of the desiccant getting into the airstream, so they don't have that issue. You know, as long as they maintain the equipment properly, you're not going to see anything. So, and in fact, there's actually probably been more comments back that they do like the fact that it's killing bacteria and viruses. That's kind of a nice.
Invariably, that's where stuff goes sideways for us. You know, in the course of the 3 days here, I couldn't tell you how many shutdowns we talk about because, you know, air monitoring goes sideways on them, you know?
Yeah.
And to me, one of the things that I had never seen in my time at Softgel was an environment problem. But, you know, to be perfectly honest, I thought we were lucky, but it turns out we were killing them. Yeah, okay,
exactly,
good.
Yeah.
I got it. So, I mean, when the guy, how do you calculate a moisture load? I mean, you ask them, like, where do you start? At the process? Where do you start?
Yeah, usually I'll ask them, you know, what kind of capsule are they looking to produce? You know, I mentioned before 24 oblong, so take that for example. You know, if they tell me that they want a 24 oblong, then we're going to look at the encapsulation machine itself. You know, what die size are they using? And then that's going to give us a number of capsules produced per hour. And if we look at that capsule production per hour, and then we look at what's the weight of it when it comes off of the die and then starts going into the tumble dryer, what's the moisture content? What does the moisture content need to be at the end of the tumble dryers before it goes into the drying tunnels? Take a look at that moisture content and the difference there, and then multiply that by your capsules that you're producing per hour. That's going to be one factor of our moisture removal that we need to do. On top of that product load, we're going to be looking at the infiltration, the permeation loads, people, you know, and again, how many times is a door opening and closing, and that'll be a contributing factor to how much moisture is going to want to gravitate into the space. And then also looking at maybe pressurization for the room too. If you want a positive pressure on the room, we're going to need to bring in a certain amount of makeup air for the space as well. And so that's kind of, those are some things we're going to look at in encapsulation, and then we'll look at drying tunnels the same way too. How many capsules are you producing per hour? And then the desired moisture content when it leaves the drying tunnel at over, say, 24 to 72 hours of drying. So.
So you don't use the moisture concentration in the gel mass to start your calculation? You know what I'm saying?
Yeah. Oh, yeah. Yeah. We're going to definitely look at that, and
right.
and that yeah, that'll be the beginning, and then there's going to be a percent solids that you're going to have as you as it goes from that starting point to the end of the tumble dryers. So so if we take a look at that and then look at that moisture content, we'll have a certain grams of moisture per capsule that we need to remove, and then it's just a matter of how many capsules are we actually producing in the machine. So
what's interesting is, let's just say for example, and again, I only asked this I've gotten burned by it years ago myself, and I think it was pretty much our infrastructure there was pretty bad. Mm-hmm. But when you do get some contaminant into the lithium chloride, how do you normally deal with this? I mean, I'm sure this happens. It happened to us with alarming frequency because I think it was ignorance.
Yeah.
All right, but I'm saying in general, so how do we deal with something?
So when you had a contaminant, was that like the oils you're saying?
It was the oil.
Yeah, it was the oils.
Let's keep it simple.
Yeah. I mean,
is this a fair question?
I mean, I would say that we don't see it affecting too much with the ability to remove the moisture from the air. But yes, if you do have the oils in the airstream, you're probably going to be filtering it out in that side stream solution filter that we have now.
Okay.
So that those oils will end up on that cartridge filter. So you might be just changing that filter more often.
I got you.
You know, but you can also look at maybe if it is too much, you can look at putting maybe a charcoal filter on the inlet air, and those charcoal filters will help reduce the amount of oils that are getting back into the airstream or into your system. So
is that the recommendation customarily?
Yeah. That seems to have helped some customers. They put some charcoal filters on the inlet, and they're not changing them very often, and anything that does get into the system seems to be not affecting it. So that seems to be a pretty good approach. So
I think people are aware too, because let's face it, breathing in vaporized oil is not exactly healthy either.
Sure. Yeah.
So I'm thinking, what I'm saying is what I've seen, I think, was that happened out of, let's say, not negligence but ignorance. Right? Mm-hmm. So it sounds to me like the filtration system handles that. So it's nothing more exotic than that.
No.
It doesn't require a desiccant change out or anything like that.
No, not at least with the liquid. I haven't seen that where people need
great.
to change out the whole liquid.
So the other thing is, what other infrastructure could you, in other words, if you go in and all of a sudden this guy has this great aha that this is what he needs, and after your discussion you say, okay, what sort of infrastructure does he have to have in place? Is there, what kind of utilities are you looking for?
Typically we're going to have, if you have chilled water as a cooling medium, we're going to need some sort of coolant to cool the liquid desiccant for on the conditioner side. If not, we can always just supply a packaged condensing unit and go that route. But it would probably be preferred if they have a chilled water system that's usually easier to control too, is with chilled water. And then on the heating side, we're going to have the regenerator that's going to be regenerating that desiccant. It needs heat. So we need either hot water or we need steam, and it's low pressure steam. It's going to be 30 pounds steam or lower, or hot water anywhere from 160 degrees Fahrenheit to 200 degrees Fahrenheit works for regenerating the desiccant. So if they don't have hot water or steam, well then we can add in a hot water heater, gas-driven or electric, to produce some hot water for our system. So.
And the reason I asked the question is, Softgel by design has got a reasonable good size footprint, but a lot of folks are working in areas in chemistry that require these sorts of extreme controls, and by design they're a heck of a lot smaller. So the reason I ask is, you go into a guy who's in he's got a contained suite in an industrial complex in a small place. The odds of him even having a chiller is pretty slim. So what I'm saying is, this thing comes in a package that we can just deploy.
Yeah, it's if it needs to be what can be a range of it. It can be a package system, or it could be comes in pieces and you need to assemble it back in place in the plant. It's they're not standard units, so they're going to be built per the application. So and like I say, if you need a condensing unit, then we can package it with that, and that can be the cooling medium or a package chiller, whatever it needs to be.
So in other words, on a one-shot deal, if he's trying to run a product, he can. This thing can be put in place on a small area. I mean, just give me a sense of it. I mean,
oh yeah. I mean, if you had, let's say you had 2 machines running, 2 encapsulation machines, then it is going to be a smaller system. It might be, 6,000, 7,000 CFM, and
we're
that can be
talking
a
about
package.
half the size of this room, pretty much.
Yeah.
Okay.
Yeah, definitely it would fit in a space this big. So So
The reason I ask is I can't tell you how many places I've walked into. I've seen a window air conditioner running in the guy's room. Try to explain to him the basic concept doesn't work.
That's not going to work. No, it's much bigger than that. That's for sure.
But on the same token, trying to explain to him that he's not really going to get where he wants to be.
Right.
So I think that's important. Optimal temperature and humidity conditions that most soft gel guys hold are what?
Yeah, encapsulation, you're going to be at just about 70, 72 degrees Fahrenheit and 35% RH. And the same goes for in the inspection areas as well, and packaging. And then drying tunnels are going to be right around 75 degrees and basically 20% RH. So.
Okay. Well, Mark, I want to thank you. If there's no further questions, thank you very much.
Yeah, thank you.
Take care.
Pharmaceutical Processing, in conjunction with INTERPHEX 2016, presents INTERPHEX Live.